Hello, everybody. It is Mike Levin on Monday, March 1st, 2021. And started to make my journal entry, and I figured I'd just jump into talking about stuff because I remember exactly where I left off and exactly what I wanted to talk about, which was HTTPX for concurrency. Yay, but necessary? Really parallelized? And the answer to that is no. I'm making good on some perhaps false information I gave out yesterday that HTTPX was doing parallelized activity. It was actually just doing concurrency. So what do you do if you want real parallelism under Python? Well, the keyword you want to look for is multiprocessing or multiprocessor. You're making use of multiple CPUs or multiple cores in your CPUs. And alternatively, multiple machines out there in the cloud, or there's all kinds of ways this can be sliced and diced. But the point is it's referring to real hardware. So that whole trick of splitting a task up over time that I talked about yesterday is actually true, because there's true parallelism where things can be split up over time because there's enough slots there to take these jobs, as many slots as you have processors. I drew it oddly here, but I will start a new diagram later when I get to different ideas, but I'll show you how I found this wonderful code here yesterday that we talked about, or it wasn't yesterday, it was the last talking head video I did. And I talked about how much I liked this and discovered how to use HTTPX from within there. And then I pasted it into a Jupyter notebook like so, and was able to quickly prove their code worked by just doing this. It's a really good feeling. That little piece at the top I had to put in there to make the event loop model in Python support nesting so that it behaves well in Jupyter Labs. And otherwise, the event loop it wouldn't be available and you get an error. So it's a nice little technique, and I can see how many stories were in there. And then I did some assignments and basically demonstrated using both the responses, the request object with list comprehension, and the HTTPX package with list comprehension to fill a list of response objects. And so I guess to do that, I guess I really can do that here. I just gotta, because this one is the thing that populates those URLs. We import requests, and we can apply requests to a single URL to remind you how that could work against a list. And then we can populate every member of a list with a response object sequentially. It took that much time. We can also do it asynchronously. That took that much time. You can see the advantage even of just concurrency. So the answer is yes, concurrency is worth it even if you're not getting true parallelized behavior. But what about when you need it and you want to address your real hardware? So I went researching, and what I found was that, well, this is context management. This is going to come up soon and repeatedly enough that it was going to be the next thing I wanted to talk about. I went looking at for the Dask package, you can use the Dask, the popular Python package for accessing your parallel hardware capabilities of common laptops or whatever you're working on these days, or of multiple resources in the cloud. And people are using Dask for that these days, so much so that it seems to be part of my retooling story. So, why this video? It's because either both Dask and the library I'm discovering that makes Dask not really necessary if you're just doing a simple map reduce. To jump ahead, I went through this learning process where this person's saying, I'm trying to do it this way. And then people are saying, well, that's not really what you're looking for. All you need is the multiprocessing and multi-threading packages, which are standard Python library things. Yay. And they're saying, see my answer. So I followed that see my answer. And the top of this was interesting. But as these things go, there's not even an upvote on it. The final thing I really want to show you is import requests, right? Our old familiar friend with the API we know. And from multiprocessing, import pool. Okay, and here's our context manager again. I told you we're going to be seeing that with open pattern over and over in the examples you're going to be seeing with me, because it's a wonderful way to do these things. But it's really just taking a file that's full of URLs and setting the URL object, just like we're doing here. We have a URL object that we're iterating over. So their example opens much the same way. And then here's the point of entry. Remember how I talked about this example? Here's the OO way of doing it with some interesting point of entry methods. The much more common to encounter point of entry method is if dunder name equals dunder main as a string. So it's weird. It's a so Python type of thing, and it doesn't make sense unless you know Python's internals and what they're really accomplishing here. And that is, this is just as if these were outdented and that line wasn't there. If you ran this script, it's going to run those just as if it just encountered them sequentially. But because every Python.py file is also a module that can be imported by other Python.py files that can also be modules, the thing that prevents everyone from running each other's codes are line like this. Everyone from running each other's code accidentally on import. That's what would happen. So if you imported the py file that this resided in into another py file you were working on, this would execute. However, because this is here, that prevents that. But if you're just sitting there in, say, Jupyter Lab executing code, this will run just as if it were sequential. And we've already imported requests over there. And so we're not sitting on top of that, text file. So we don't really even need that. We have an already populated URLs object. So if I take these two things, I should pretty easily be able to test this approach in that same Jupyter Lab, right? See, I'm just going to be recycling things from the last lesson. I paste these things in here, and I position my cursor there, and I do Control-Shift-, which I do believe is a cell split. I'm getting the hang of this stuff. So I'll just, I have an import to do, so I'll hit Escape key and A for above, position my cursor in there, and import that, dragging tabs around. The magic fairy dust, right? You're always looking for what the magic fairy dust that gets sprinkled into the notebook or whatever is, and in that case, it's that. Now I can load this function into memory. Now I can do this, and this will be an updated example of using true parallelism to carry out those same URL fetches. Although they're populating this specific object they're creating differently than me just making a series of response objects in a dictionary or in a library or in a list in that case. So they're doing something a little bit different, but what we're encountering here, this long asterisk, is exactly the opposite of what one would expect if you were to pull out all stops and use the multiple cores that might be available in your machine. It shouldn't be taking this long. However, perhaps there is overhead that is being instantiated with a lot of startup cost for the first time. Oh, well, no. They are interfering with the URL thing there. So I'm going to hit escape and 00 to actually restart the kernel. Control-Shift-R is going to restart the kernel and clear all output so that I can make sure we're back to a nice clean state. And then I'm just going to execute these two things again. And then I'm going to think this through more clearly and make a better example for you and teach you to read what you copy and paste. For URL in URLs, URL equals appending HTTP to the beginning. No, not at all. The URL is a fully qualified URL already. Try. Well, try is nice, but these URLs are going to be reachable. So if there's an error, I want to see it. That gets rid of all that. And now we're down to this. And now I can, make it, more traditional of return a list. So we'll say, return me equals a list. And each time you create a response object from a request.get, you don't need any of that stuff. You return me.append the object you just created, and you be very optimistic about its success, and then you return me. And yeah, that's gonna, if I have these different responses, doing it the old sequential way, URLs is not defined, so I need to execute this line. This is the thing about notebooks. It becomes, you have to remember the order you did it, and if you are working that way, you're working wrong. But here's sequential. Here is concurrent. And here is multi-CPU. What am I doing wrong? Do I have this thing? Yeah, that's what that function's called. It takes the input, which is a list of URLs, and then for each URL in the list of URLs, it requests .get the URL. And it's using a timeout, which I don't usually do, but okay. And then I'm appending to our return me object what was just created. And then I am returning the list of response objects. Okay, so if name equals main, I can probably take that out because we're in a notebook. You don't really need that so much in a notebook. I'm going to try and stop this task without interrupting the kernel. Now, because we're dealing with multi-threading, not multi-threading, excuse me, multi-processors, that's probably not going to work. We're going to have to interrupt the kernel. Control-Shift-R will do it. In fact, it gives me the double benefit of resetting the kernel and clearing all outputs. So I just wait for that sort of flashy event to happen there, re-execute those. Okay, I can get rid of some of these things we don't need anymore because it was for lessons, and make it so that you execute them in order. Okay, so the demos, sequential, asynchronous, We don't need our little demo of splatting. We import our library. We create our function. And now we look to see why in the world this would, oh yeah, I wanted to get rid of this because we're in a notebook context. We don't really need that anymore. So we just eliminate that as part of the possibilities. And now we just read this and make sure we understand we're really doing what we think we're doing. So we're creating the P object. The P is from pool with 4 processes. Maybe I don't have 4 cores. Maybe I only have 2 cores. I'm on a modest little i5 here. So let's be honest. If I get 2 CPU parallelism and something near times 1 point something, because overhead, it will be a success. It needs to actually run. So that's one fix I've made. And you know, we're talking about these objects I'm making. It's arbitrary, but since I have responses, A responses for asynchronous, I'll have P responses for having done it with multiple processors. So we're invoking the map method of the pool of an instance of the pool object designed to hit 2 CPU cores, to take this function and to apply and to map as input to it this list of inputs. So one thing that already occurs to me is that if this is already looking for a list-like object and it's expecting a list-like object, this function doesn't need to work on the list. It just needs to do it. In fact, this whole thing may be extremely overcomplicated. I may be able to do just request.getURL right here and forego the function. And we're saying P responses equals the mapping of this list over this function request.get. It'll be fed in to that function, right? That should work. Hey, that worked fast. And that was with multiple cores, in my case 2. Let's see what that response looks like. There is your 10 response objects. Using the requests library, I suppose we can use the concurrent equivalent and fully complete this test. And that's a 2-line thing. I don't even know how I would go about that. Maybe readers can chime in. But I basically use the requests object over multiple processors. Now I could use the HTTPX object because it's API compatible and it can really be this easy. I'm populating the same, oh, something wrong. Did I not import it? Reason attributor, pickle local requests. It's on close. Interesting. Yep. I do not know. Again, it's above my pay grade. I could probably go research this. However, what I think I have here is a bankable success. I've done my demonstration. While I didn't cover every aspect of the matrix I'm drawing here, where you have a vertical axis and you have a horizontal axis and you have CPU. Let's see, how would that work? Concurrent. Parallel. And let's let's see, what are those other two things I'm comparing this in this case? Oh yeah, HTTPX and the request object. So I guess that would look something like this. So we have I always stumble over the colors. I'm going to eventually switch my drawing program. I'm just pretty comfortable in Art Rage right now. Apparently not comfortable enough, but we've done the request object in concurrent and true parallel mode between the last talking head video and this one. And we have done HTTPX in concurrent mode, but not true parallel. So this is the one place we have not really covered yet in these two videos. However, I still bank it as a success about talking about how to take advantage of the multiple CPU cores. I don't think I'll get into Dask in this video, and I don't think I really even need to. That will come up when it has to. It's not as fundamental a part of my retooling as, you know, I guess what I was talking about here that brought me into that whole discussion is multiprocessing. What did I end up using in my notebook? What down at that simplest level? By the way, I did not even use this, so we have distilled the multiprocessor example down to these 3 lines of code. I guess I can do Control-Shift-M for merge. No. Oh, Escape Shift M, not Control Shift M, so merging. So it's really these 3 lines of code. This is showing the output. So we have demonstrated this thing that is built up as so difficult in the Python community. Oh my goodness, how can you use multiple processors? And I think I'm going to just go like this. Because, you know, it helps you think about it. You're mapping over your multiple processors, request.get, this list of URLs. And this word looks a little like processors, so maybe that's the one bad thing in my example here. But so what? It is P responses for using the multiple processors to get the responses. And here it is with using the asynchronous async IO with HTTPX. And here it is the old-fashioned way with just list comprehensions. And wow, I dare you to show me anyone who lays out the multiple paths to concurrency and parallelism clearer. Oh, maybe I should make comments. This is sequential, which you might say is classic Python. This is concurrent. And you might say that's, you know, thanks to Python async IO from standard library and HTTPX. Okay, so it's combining 2 little pieces of magic there. And then this one here, and you know, actually there's an import, so we can't count this line towards the complexity of the multiprocessor approach. So escape shift no, I can use my cursor there. Control Shift minus for splitting it. So the comment here is multiprocessor, which is true parallelism, which is taking advantage of your multi-cores, right? So that's the three approaches that you will often encounter in doing things like building a list of response objects. And just to really hit home, something I kind of have been meaning to do is to show you how you can, reach into that and show, if you wanted a list of resolved URLs, X for X in, and X is going to have a property called URLs. And so there you can show the fully resolved URLs. Sure, it was URLs to start with, but if it did any auto forwarding, this is going to show you that, the end of the forwarding chain. I guess other things I could show you is I think it was response code. Status code. Yeah, there's your status codes, coming back as a list out of your response object. So I guess that pretty much wraps it up. That's a pretty powerful video there. Clarified something from a prior video, and now we have just 3 techniques at our disposal when we tackle projects, and we can just sort of hop between them pretty easily. Thanks for joining me. Hope to talk to you soon, and don't forget to subscribe.